Hello, my name is KSteinacker. Today in this edition of KI Knowledge Integration, we're going to be talking about an audio amplifier in a cellular phone. We're going to be talking about it in three different topics. First talking about it in linear systems analysis and talking about how we use a transfer function to come out with an output voltage that has a phase shift and multiplied by an amplitude. We're going to be talking about it in microelectronics, where we investigate the gain of different MOSFET transistors and also the output impedance. We're also going to be talking about it in the subject of electromagnetics and how we use a magnetic circuit to drive the actual speaker for the audio output.
We can now begin our discussion of the audio amplifier at the systems level, and we just need to talk about what this is doing. So we have the same amplifier. We recognize here that it's just this input, and it goes through a linear time invariant system. It's simply a ratio of the output and the input and the input. Know from Euler's identity. And this is our kind of Euler's expansion of the cosine expression. So we feed that into the linear time invariant system, and what we get out is a half h to j omega naught e to the j omega t plus a half h to the minus j omega naught e to the minus j omega naught t. Because we know the property of conjugate symmetry, we know that we have a Vn that is real valued. Know that the magnitude of h of j omega is equal to the magnitude of h of minus j omega. And for the phase, we know that the phase of h j omega is equal to negative phase h of negative j omega. On the whole, we have a amplitude multiplied by this magnitude of h of j omega naught, and we also have a phase shift.
In our first MOSFET that we encounter, this is a common source topology. Let's look real quickly at what happens when we look at this first MOSFET transistor and if we increase our VB value. So we have our voltage gain as a function of the transconductance and the output resistance. We have some simple equations here, and let's know that when we look at the large signal analysis of the transconductance, it's going to be proportional to just VGS minus the threshold voltage. Output resistance, R naught, is going to be proportional to 1 over voltage gain to source minus the threshold voltage squared. When we're increasing VGS, making it go up to equal 0.7 volts instead of 0.65, our VGS is increased, our voltage gain is going to go down. And moving right along, we can look back at our circuit, and then we can start to investigate the small signal model for these MOSFETs to see why we have this common source here, and then also a source follower transistor here. Just looking at that first stage, we have a gain that is minus GM1 times R naught in parallel with R1. We say here, so the output resistance is about 5 k ohms. You know that the voltage drop across this resistor, our load, V out, something like, worst case, 4 ohms over 5,004. It's a very small number ratio. Because of this feature that we have such a minimal voltage drop across the load when we have this big output resistance, we add another stage, and we add this source follower here. Because one of the characteristics of the source follower is very low, our out is very small. This is the output impedance, which is going to be R naught 2 in parallel of 1 over GM. GM is usually a very large value, so 1 over GM we understand to be small. condensed into one here. We have an R out that's roughly equal to 1 over GM2, and our load about 4 ohms or 10 ohms, 100 ohms, depending on the speaker. And this gives us kind of our best case of a good amplification and a very small output resistance. Now, what do we do with the output of this whole system? I'm obliged to say something about the electromagnetics portion of this. So what we have here is a magnetization curve. It's nonlinear. You have the B field and the H field. They're analogous to current and voltage. Here's just a generic multi-node and 2-loop magnetic circuit. You generally have this Ni, which is analogous to electromotive force, the H vector and the B vector, and then the H vector is analogous along any one of these links as voltage, like resistances as well, and taking into account this S is going to be a mu naught value or a mu value of the relative permittivity of the magnetic material. And so we have that output signal from that amplifier, and that's going here, and you have electromotive force, or an MMF in this case. It's going to generate a B field one way or the other to move this coil and generate these sound waves. It's the same thing. Again, we have our Vin. Talked about that. Goes through the audio amplifier. It gets our V out. That's fed to here, and we have our Ni. That's going to make an electromotive force. It's going to cause our B field or H field to go here. It's going to draw in or out this whole cone here. It's going to either go in or out at a given rate, a given frequency that will generate the sound waves concentrically. And that concludes our discussion.
I hope this video was clear and informative, and I'll see you next time for knowledge.